All right, so welcome to the last talk of the week. That's going to be on neutrino physics, and I think exploring the energy frontier of muon beams is our title, but probably also yours. So I'll give you the 50 minutes or so sign, depending where you are. The floor is yours.
Okay, thank you. Thank you everyone for coming. I know it's a Friday afternoon and you probably would prefer to go to the city rather than sit here for a talk. I apologize, I'm leaving tomorrow, so just wanted to see if I can give a talk before I leave. Initially I gave the title is probing the neutrino mass mechanism at Muon collider, but I decided to make it a little bit broader, and I'll discuss first some standard model physics with neutrinos, and then some BSM physics at Muon collider. So thanks to the organizers for having me here. It's my first time here, GGI, so I got a t-shirt. It's really nice. Okay, so let's get started. So we do know that the neutrinos are the kind of the last frontier of the standard model. They're the least known, and they're very special because they're the only particles that oscillate between the different flavors. And that means that the flavor eigenstates are not aligned with the mass eigenstate. If you just calculate the oscillation probability in the two-flavor approximation, you get a very simple formula that looks like this. So you have the sine square of 2 times the mixing angle, and then sine square of the mass square splitting times the oscillation length divided by the energy. So if you, and we have measured the oscillation probability to be non-zero for all 3 different flavors between each other. And that means that at least 2 of the mass eigenvalues must be non-zero, and all 3 mixing angles must be non-zero, right? So, and there's already evidence for BSM physics, because there's no way in the standard model you can accommodate this feature of the neutrino oscillations or giving mass to the neutrinos. Now, this on the 3 neutrino oscillation paradigm, it is entering now precision era. If you look at the progress over the last couple of decades or so, how the different values of these mixing parameters they evolved. With having order 1 precision now to percent level precision. So we have really made remarkable progress in all the 3 oscillation parameters, in the 3 mixing angles, the 2 mass square differences, and also the CP phase. In all these sectors, there has been remarkable progress over the last 2 decades. So the question is, once we measure this to whatever precision we want, then what do we do next? Okay, so where should we go? Do we just say that, okay, this is done, now we understand everything about neutrinos? And I will argue that that's rather the contrary. There are many open questions in the neutrino physics sector, and just measuring the parameters to any amount of precision you want, that doesn't really answer all the questions. Okay, and so here is a list of the open questions. Also, Chris showed it in his talk. He had 14 questions. I have reduced them to 11. Well, because I like 11. And also have color coded them in 3 different ways. The first 3 questions, they're kind of easier questions to answer. Well, easy means we need a $3 billion experiment to answer these questions. But we know that the answer is out there, and it's within our reach. In the next 10 to 15 years, we would know most likely the answer to these 3 questions. What is the mass ordering, normal or inverted? And what is the octant of the atmospheric mixing angle? It is more than 45 or less than 45 or exactly 45. And is there a CP violation, either delta CP 0 or non-zero? Okay. So both the Juno, Hyper-K, and Dune, combiningly, I think will answer these 3 questions in the next 10 to 15 years. The other 3 questions in orange, they are kind of they're of course more difficult than the first 3 questions, but they're still within our reach in principle, if nature is kind to us. But the absolute neutrino mass scale, cosmology is already giving us some hints. And we do know from large scale structure data and BAO data that the sum of neutrino masses have to be smaller than something. Right now, the value is around 0.1 eV, depending on which data set you use. And in the future, this is going to get more and more precise. There are other experiments coming up. In principle, CMBS4 can really answer this pin it down, but even without that, with the DAISY, already we are getting some hints for the normal ordering of neutrino mass, right? And then the other direct probe would be the beta decay. This is just looking at the endpoint of the beta decay spectrum. And Catherine has the best bound at the moment, 0.45 eV. That is nowhere close to the cosmology bound, but that is a direct measurement, and there is no ambiguity over there. And they are planning to improve it to 0.2. And in the future, there's another experiment called Project 8 that can go down to another order of magnitude, 0.04 eV. So that will really pin down, hopefully that will pin down the absolute neutrino mass scale. But the other species of neutrinos, well, there are dedicated experiments going on. The whole sort baseline program at Fermilab, they're trying to answer this question with the the SBND experiment and the microboon we just finished running, and then Icarus, and then in the future Dioneer detector as well. There are also for larger sterile masses, you have the beam dump experiments, the meson decays, and eventually, if you are going to TeV range, then colliders can really help answer this question. So I put the colliders in bold because the topic is colliders here. So I would like to mention few of these open questions that colliders can really answer for us. Similarly, for about the mass mechanism for the neutrinos, is it Dirac neutrino or Majorana neutrino? That could also be answered by colliders. In addition to other experiments, the most smoking gun signal, I would say, would come from double beta decay. If we measure a signal, positive signal in double beta decay, that would really mean that neutrinos are Majorana particles. There's a no-go theorem on that. And also, if you measure the cosmic relic neutrino background, then also you can definitely tell whether it's a Dirac or Majorana because the rates are just factor of 2, and that you cannot miss. But that is very challenging to measure. So at the moment, we don't know whether any other way we can probe the Dirac or Majorana nature. So colliders can really help us there. So I'll give you some concrete example of that later. Now, the other questions here are harder questions. That's why I put them in red. We may never know the answer to those, unfortunately. And there's no single observable that we can have to answer these questions. So indeed, multiple observables across multiple frontiers. We need data from energy frontier, intensity, and cosmic frontier all together. And maybe then we might have some answer to these questions. So I'm not going to attempt to answer those questions here. Okay. But yeah, so the bottom line is that the colliders can really help us answer some of these questions, if not all of them. Yes. Right. So for example, the heaviest neutrino can decay to lighter neutrino plus a photon. It's a radiative decay. There are constraints on that, of course. The cosmology constraints are there, but those limits are around 10⁹ seconds or so, which is much less than the age of the universe. So we would like to know whether they're absolutely stable or do they really have decay. And if they decay, they could actually also leave other imprints. Like in oscillation experiments, the oscillation probability usually doesn't depend on the Majorana phases. But if the neutrinos decay, then it turns out that there is a decay term containing the Majorana phase in the oscillations. So even the oscillation probabilities could get changed, and then all the 3 oscillation paradigm that we are dealing with, all the predictions of that could actually change. So there is some sensitivity to that also coming from neutrino decay. So there is some hope that we might be able to answer that question. Yes. All right. So let me start with an old example, how colliders really help us understand neutrino physics better. I'm sure you all have seen this picture. This is in PDG. This is the LEP measurement of the Z. At the Z pole. So you just look at E plus E minus hadrons, look at the cross section, and then this cross section depends on the total width of the Z, and it also depends on the partial widths into the hadrons. And in that way, so if you have more than 3 neutrino species or less than 3 neutrino species, you see that this curve is very different. And you can see the error bars over here. At the Z pole, the error bar is very precise. They actually have magnified the error bars by 10 factor of 10, just so that you can see them. So it's a really, really precise measurement. And that has conclusively told us that the Z cannot couple to more than 3 species of neutrinos, as long as those neutrinos are lighter than the Z, right? In fact, so apart from this classic measurement, LEP has also done another measurement. This is a measurement in the monophoton channel. Just do E plus E minus 2 nu bar gamma. And again, so if you look at the cross section of this process, you see that if you have more than 3 or less than 3, then the cross section really deviates much from the data. And again, looking at the Z pole here, they can precisely tell that you must have only 3 species of neutrino, not more, not less. So this is one example where this is really telling us that we cannot have more active species of neutrinos. And in fact, you can use the same measurement also to rule out sterile neutrinos if they couple significantly to active neutrinos. Okay, I'll show you some bounds later on that. So there is already historical evidence that we do have useful information coming from colliders on the neutrinos. Now, coming to a more recent example, we have this fantastic experiment called Phaser at the LHC. And for the first time, they have seen neutrinos coming from the PP collisions. Okay, and this is a remarkable achievement. And in fact, not just a proof of principle, but they can also do some measurements here. And this is one of the recent papers from last year, where they have given the measurement of the neutrino nucleon cross sections, okay, in the region where there was no data before. If you look at the plot on the right here, there is a lot of data in the low energy regime here, coming from mostly accelerator experiments. And there is also data in the high energy regime coming from astrophysics, from IceCube actually, looking at the high energy neutrino interactions in IceCube. But there is no experiment in the middle here. And so there are only some extrapolations of this neutrino nucleon modeling, these Bodekang models. But now Phaser has really confirmed that this model really works even when you extrapolate to higher energy. So they're really filling this gap between the low energy measurements and high energy measurements. And this is actually crucial. This plays a very important role in validating these models. And these models are the inputs for the oscillation experiments. Okay, when you try, people put them into Gini, and then they try to model the nuclear uncertainties. And this is crucial for the success of the oscillation experiment. So here, the colliders are really playing a key role in validating some of this modeling. Okay. Yes. So not one TP is crucial, but to validate the modeling of these neutrino nucleus interactions. And so if you're using this Bodekang model, you would like to know how the model behaves across different energies, right? So so exactly. So you can remove some of the degeneracies there. That's the idea. Because the model has a lot of free parameters. And what you do typically in Gini, that you tune these parameters to fit some data, right? Now, if you have more data, then you can, you need less tuning, right? And no, this will be at 1 TB, this will be DIS, right? So there is still some nucleonic form factor uncertainties coming into picture. So if you are really, so these experiment Phaser, they're using tungsten, I believe. So we don't have much data for heavier nuclei, even at low energies. Only have, like, people have reproduced, people have models which can reproduce the data up to maybe carbon, but not more than that. So if you have data, data is always useful, right? No matter in what regime you have. So the point is that, okay, I'm not an expert on the nuclear physics modeling part, but all I know is that they can now use this data to do better tuning for the models, which can be used as an input to the experiments. Yeah. Right, but no, but you're right that you're not directly using it, because the direct measurements you need are in the GeV range, GeV to maybe 10 GeV, 20 GeV range. But when you have a data point at higher energy, you can do the extrapolation, and then you can test the model at different energy scales. The validity of the model. Right. 40 TeV. Okay. Uh-huh. But that's a neutrino. But that's electron proton. Right. Right. Yeah, I mean, this is just the beginning, right? We are not there yet. Yeah. Yeah, yeah. No, that's true. Yeah, I mean, yeah. No, but this is with a new mu. The right plot is with new mu. So I don't think there is hera data on new mu, right? Right. Yeah, but that also, I mean, there are something that you need to test, right? We cannot just trust on the universality here. Yeah. Exactly. Yeah, it's a complex. Right. Right. Exactly. Yeah. Yeah. So that's the next slide. Yeah. Okay. Any other questions on this? All right. Yeah. So with a muon collider, how much better can we do? Okay. So yeah, here is a plot from a recent paper, the neutrino slice paper by Carlos and company. And so here they're showing the same plot essentially, but now on top of it they have the projections coming from a muon collider. And as you can see, the error bars would be much smaller here. Okay, so you can in principle do much more precise estimate of the cross sections in this gap region. So this is the error bar for the phasor, just for comparison. This is the neutrino slice. They're using the neutrino slice, right? Yes, just a slice of the main detector where, from muon decay you get the neutrinos, and then you can use the interactions. Yeah, so you can ask him. You mean like just like this neutrino lighthouse idea, or? Oh, like the phasor? Oh, okay, yeah, of course, yeah, you can do it at a further distance. Yeah, in principle, yeah. That in another experiment. Yeah. This is for free. Because this is essentially there. You're not having a new detector or anything. I think you just need some detector design change. I don't know the details. So this is a very recent paper. Yeah. Yeah. So you can already get this for free, essentially. Yeah. Yeah. The main detector, right? Yeah, exactly. And you can also do other precise things. For example, this recent paper by Andre de Govia and Adrian. So they showed that you can also measure the sine square theta w to very high precision using the elastic neutrino electron scattering. Okay, and this neutrino coming from the muon collider. And so they have shown these three different benchmarks here: 250 GeV, 1.5 TeV, and 5 TeV. And you can see that the error bar, is again very impressive. It's much better than any other experiment being proposed at the moment to look for the running of the sine square theta w. So these are just some examples. We saw that okay, not only we can do precision standard model physics, but also they can be sensitive probes of BSM physics. For instance, if you had some BSM interactions going on at some high energy scale, then you can also be sensitive to that effect here. So this is really impressive. All right, but that's not the topic of my talk. So I'll mostly focus on the neutrino mass mechanism and tell you what muon collider can do. This question. Okay, so just as a reminder, we cannot explain the neutrino mass in the standard because of various things. The first thing is that we do not have a right-handed partner, so we cannot write a Dirac mass term, as simple as that. And then you cannot also write a Majorana mass term within the standard model gauge group within standard model particle content, because the neutrino is a left-handed doublet. So if you write a Majorana mass term that transforms as a triplet, that breaks the sp2 invariance. So this is true to all orders in perturbation theory. Okay. Now you could imagine that maybe some non-perturbative effects could save us. We do know that there are non-perturbative Spalaron effects which do break lepton number, but they break only in the B plus L combination. They preserve the B minus L, which is an accidental global symmetry of the standard model. So these also cannot generate neutrino mass. And then finally, as a last resort, we know nothing about the Planck scale physics. So, but we do know that any global symmetry will be broken at the Planck scale by some quantum gravity corrections. So maybe they can save us. Well, it turns out that even if you write the simplest, the lowest dimensional operator, the dimension 5 Weinberg operator, and then take the quantum gravity corrections, they will go like V square over M Planck, or V is the electric wave, right? And if you just plug in the numbers, you find this is 10 to minus 5 electron volt. This is actually small. This is in the ballpark, but this is actually smaller than the atmospheric splitting. So we cannot explain at least atmospheric splitting with that. So there is no way in the standard model that you can generate mass for the neutrino to explain the oscillation data. So and the point that the neutrino mass is very small compared to the other fermions, there might be something beyond the standard Higgs mechanism that could give mass to the neutrino, right? So essentially, you'll have some new scalar, or you have some new fermion, or gauge boson, or a combination of these, and these are the messengers of the neutrino mass. So the hope is that if these particles are accessible to the colliders, then we might be able to produce them directly and to see their effect and to understand the neutrino mass mechanism. Okay? So that's the idea here. Okay, so I'll start with a simple case, which is known as the heavy neutral leptons, HNLs. People also call them right-handed neutrino, sterile neutrino, heavy neutrino. There are many names for that. But essentially, they're standard model singlet fermions. Okay, and so this is the simplest possibility for generating neutrino mass. As soon as you add the right-handed neutrinos, then you can write a Dirac mass term. But also, because these are standard model singlets, you can write a Majorana mass term for them. There is no breaking of gauge invariance here. So you can write this Yukawa-Lagrangian that then after electric symmetry breaking, it gives you this mass matrix. And in the limit when the Majorana mass term is much larger compared to the Dirac mass, you get what is known as a seesaw, that the light neutrino mass is given by the Dirac mass square divided by the Majorana mass. Okay, and that's why it's called seesaw, because the lightness of the light neutrino can be explained by the heaviness of the heavy neutrino, right? And as I said, this is the simplest tree-level realization of the Weinberg operator. Okay, so the key question here is, what is the scale of this right-handed neutrino, or what is the scale of scale Mn here? So traditionally, when people wrote down these models when people invented the type 1 seesaw, they were motivated by high scale physics. Okay, the motivation was coming from some SO10 grand unified theory, where all the standard model fermions as well as the right-handed neutrino are part of the same fundamental multiplet, the 16-dimensional multiplet in SO10. So naturally, you would expect that the scale of the seesaw would be very high at the gut scale. But if you're doing a phenomenological bottom-up approach, then you cannot really tell what is the scale, right? Let's say we don't know anything about the high scale physics. We are just looking at in the low energy effective theory, then we can't really tell what is the scale of the HNL. And in fact, its scale can be anywhere from EV scale all the way up to gut scale, okay, in this theory. Now, depending on what you want to explain, what you want to solve, you can put the scale wherever you want. And people have done that. So in the EV scale, people have tried to explain this, all these sort baseline anomalies. And if you're in the electroic scale, that is our interest here. You can probe them in colliders. And if they're much higher scale, of course, then we have no hope. All right? But is this enough, or is there any better motivation? It turns out, if you use the naturalness arguments like Michael was using the other day, you can actually show that there's an upper bound to this to the right-handed neutrino mass scale. And this comes from the following. If you just have, because these right-hand neutrinos couple to the Higgs, and we do know that it gets a quadratic divergence, just like the top quark. And you also want to explain the neutrino mass, so you do not have freedom in the Ikawa couplings. Okay, you do not have arbitrary freedom. So if you want to explain the neutrino mass, and you also want to keep the Higgs radiatively stable, then you can show that there is an upper bound on the mass of the right-handed neutrino, which is shown in this plot over here. Only this region is the allowed region. So depending on how much fine tuning you want to allow, if you want to allow for like only the correction term to be the same order as the standard model Higgs mass, then it turns out the bound is around 10 is to, I don't know, 10 is to 4 GeV or something. It's just 10 TeV. But if you want to allow a little bit more fine tuning, you want this correction to be 5 TeV, then you can go up to 10 is to 5 GeV or so. But in any case, if you don't want too much fine tuning, you cannot allow for this right-hand neutrino to be very heavy. Okay, so this gives you at least some motivation that that we do have some hope of finding HNLs at the colliders if nature is natural. Okay, I'm sorry. Alpha strong. Why alpha strong is relevant? So in the running, right? So when you do the so all these parameters have to run to high scale. So if you're testing you're testing naturalness, you are testing the perturbative unitarity. So you have I mean there's a lot of different things going on here, and so to use in the running, alpha strong is important. And of course we do know in the standard model also the alpha strong is important in telling us whether the vacuum is metastable or unstable, right? Both alpha. So it is relevant, for example, to the metastability bound over here. So this is the line for metastability at the high scale. And so if you want the standard model to be metastable all the way up to Planck scale, then you need to know like what exactly are the inputs for your top quark mass and for alpha strong. Just like same way as, or at least if you want the, yeah, sorry, no, that's fine. Yeah. In some sense, it will affect, right? It doesn't affect these lines, but if the metastability bound was somewhere over here, then it does affect, right? Then the allowed region or parameter space would be much smaller. So exactly, because when you add this extra fermion, you do know that they usually make the vacuum instability worse, right? Because they give a negative correction to the Higgs mass, right? So let me use this one. Yeah, so these three are the regions for different naturalness bounds. If you take 200 GeV, 5 TeV, or 1 TeV, I should have changed the order of those two. But and this part here is the bound coming from lepton flavor violation, because the same Ikawa couplings that you have here, you will have some off diagonals in there to fit the neutrino mass, and they will induce LFB like mu to gamma and so on. And those bounds will go like this. So this part is excluded. And then these two are the theoretical bounds. One is coming from metastability, and the other one is coming from perturbative unitarity. Just that the Ikawa should not be larger than square root 4 pi. Right. So essentially, so you can only live in this part of the parameter space. Right. So if you really want to have the Ikawa to be large, then obviously you can't allow for the mass to be large as well. Of course, you can live in this bottom part here and go down here. So the Ikawa is extremely small, and the mass is also very small. Mass is very large. You can allow for that possibly, but that will be really boring case, right? Then you can't really test anything. Everything is decoupled then. That's correct. Exactly. Yeah, yeah. So that's the assumption here. Otherwise, you can't do the RG, right? If you have some other new particles, they could change the RG and they could change this picture, of course. Yeah. So you're just assuming that up to this scale here, we don't have anything other than just the standard model plus these guys, right? But okay. So I guess the point here is that this gives us some hope that we could, in principle, find these particles at the colliders. Yes. The line on the left panel, you mean the which one? This is seesaw line here. So this is just for a single generation here, but for 3 generations it's more complicated, and that's already fitted into this, and that so that's already included in the choice of the Ikawa matrix that's being used here. So you use Kasasibara basically. Because what is plotted here is not just a thing, it's a plotted is trace of a matrix here, right? So that matrix structure is governed by the Kasasibara. Yes. Right. Yeah. Right. Yeah. And that's essentially the origin of this line, right? Yes. Exactly. All right. Okay. So now the next question is, if you allow for large couplings here and small masses, then is that theory consistent? Okay. And the answer is yes. Naively, if you expect, if you just write down the mixing, then from the CISA expectation, you simply have this formula, right? M Dirac over M Marana. And then you can rewrite this in terms of the light neutrino mass over the heavy neutrino mass. And that turns out to be for 100 GeV about 10 to the minus 6. So that's very small coupling, right? And for that coupling, you can't really hope to see much at colliders because the production cross section would be very small. But luckily, this is only true in the one generation case. And if you have two or more generations, then you can use some special textures and you can allow for large mixings while keeping the mass also small. Okay. And here is one example of that, first shown by Kostin and Smirnov, that if you take this particular texture and keep, so these terms are very small, this is like basically a column matrix. And in that case, you can show that you can essentially get m nu equal to 0. Light neutrino is exactly massless in the limit where all these perturbations are small, whereas this mixing is governed by this small m over capital M, and that can be arbitrary. Okay, so this is one way you can decouple the heavy mass from the mixing, okay, while still satisfying the Caesar relation, simply because of the metric structure. Okay. And then later, it was shown that this is actually radiatively stable, even if you induce, radiative corrections to these to these terms, it still preserves this structure essentially. So this is still possible at even higher order. And the same thing can also be achieved maybe more naturally in other variants of the type 1 CISO, like if you add extra fermions, that's called inverse CISO, and then with different structures and so on, then you can also have this large mixing with smaller masses. So you can basically treat the mass and the mixing as free parameters. That's the bottom line. Okay? And then you can go on and in experiment, you can probe this mass mixing plane and then see how much you can probe. But there is a price to pay, of course. All good things have to come with a price. This has suppressed lepton number of ovulating signals. And that you can already see from this structure here, that if you take delta M to 0, then essentially you're having a Dirac mass here, right? Because you have like these two eigenvalues will be plus M1 minus M1, and that's essentially a Dirac structure. So adding a small perturbation, just make it quasi-Dirac for the heavy neutrinos. So any lepton number of ovulation that you might induce because of these heavy neutrinos, that will be suppressed. There will be cancellation of the phase by pi. But that's fine. You can still look for lepton number conserving signals and still hope to find the HNLs with that. Now, this is true only in the minimal scenario. You can, of course, make life more complicated. You can add you can extend the standard model gaze group. For example, you can go to another U1. You can do left-right or whatever. And in those cases, you can still induce lepton number of ovulation. Not coming directly from this from the CISO, but can come from the gauge structure, right? You can have a right-handed gauge boson, and that can induce lepton number of ovulation directly from the right-handed gauge group. So yeah, so there are many things that one could do there, but let me just stick to the simplest case just for concreteness. Okay, so since the mass and mixing can be treated essentially as pre-parameters, I'm just plotting here in this plane what are the current constraints. This plot is very busy. There are various different constraints coming in here. But what is interesting to note here is that you can roughly divide this whole region into 4 different regions. So to the left of roughly MEV scale, the most important constraints are coming from cosmology or astrophysics, okay? Like from CMB, from BBN, from supernovae, and so on. So let's forget about that part because we are at a collider conference. And in the middle part here, the most important constraints are coming from meson decays or from beam dump experiments, right? So you can look for peak searches in meson decays. That's what this PINU experiment does, for example, or you can look for producing there's HNLs at some beam dump and looking for the signals of that. That's what NA62 does, for example, or T2K does. And then the most interesting part for maybe for this audience would be this region here, from roughly 1 GeV to 1 TeV, And that is the part where colliders can really help us. Those, the most stringent bounds at the moment actually come from colliders. Okay, and you can see already that the bounds coming from LEP here, this is coming from Z decay to one neutrino plus a sterile neutrino, and then this HNL or the sterile neutrino decaying to one lepton plus a single lepton. So you look for the monolepton search, and this already gives you bound, and also looking at the Z decay width, you can put a bound all the way up to the Z mass. And then beyond that, you can directly produce them at the colliders, and then you can also put some bounds. And there are bounds from both LEP and also from CMS and Atlas. So yeah, so essentially this is the part where colliders can come into picture, and they can really push down these limits further. Okay, and then beyond about a TeV or so, or maybe 10 TeV, depending on what is the center mass energy of a collider, the bounds would mostly coming from just EFT, because now you have like contact interaction, and you can look for from your operators and do precision electric physics. We're looking for deviations to G Fermi and so on, and they will give you some bound in that region. Okay. Okay, so this is the current status. Now, what is the future prospect? So this is the future prospect. Again, I have this these 4 lines over here. And so again, this is a very busy plot. But if you focus on this collider part, then there are 2 types of searches over here. One is happening in this direction, where you have low masses and there's very small mixings. In that region, your HNL is long-lived. Okay, so you do a long-lived search. Okay, you produce the HNL at the primary vertex, but then HNL travels some distance, and then you look for the decay at a LLP type of detector, and that's why you have Methuselah. You'll have SIP somewhere over there, and Phaser, and so on, LSCB, and so on. And then there is, and in the future you could have FCC-EE, and also Muon collider probably would come in there if you have a if you have put a FAR detector. And then there's another part over here. This is going in this direction roughly, and that is just a direct production of the HNL. Okay, and they decay promptly because the coupling is large and the mass is also large. So the decay, lifetime is small. So they decay promptly within the detector, or maybe they'll have a displaced vertex, but within the detector, and then you can probe this part of the parameter space. Okay. In this plot, as you can see, the Muon collider is not there yet, simply because there is no study at that time on the Muon collider. But now we do have, so I'll show you those results later. Okay, before going to that, let me just talk about HNLs at a future E plus E minus collider. Okay, and this is some study that we did almost 10 years ago, more than that actually. And the main production channel would be just coming from through the Z-mediated diagram or from the W-mediated diagram. If the HNL couples to electron flavor, then both of them will be important, relevant. But if the HNL couples to only muon or tau flavor, then you can only do this diagram. This T channel doesn't exist, right? So depending on that, the cross section would be different. Here, 2 different, very modest center mass energy, 350 and 500. And you can see the cross sections here scaled by the coupling square, the mixing square. And then you can do a sensitivity study, and what you find is that you can probe some coupling range which is not yet excluded by the LHC. So this plot is actually outdated because now the LHC bounds are a bit stronger, so they actually push down to almost this level, 10 to the minus 4 level. But the same thing now we can do at a Muon collider. So you take exactly same diagrams, just replace the E plus E minus with mu plus mu minus, right? Everything else is the same, and that's what was done recently in this paper. Right, yeah. So here again, so we are very, very modest at the time, just using very small luminosity, small center mass energy, and so on. Yeah, if you use 1 TeV, for example, for ILC, you'll get to higher values, and if you use higher, 8/1 inverse, you can go down further. Yeah. I don't know if people have done that study with higher luminosity, but it's straightforward to just extrapolate these bounds. Yeah. But now, okay, the similar sensitivity for Muon collider now exists. Again, you have the same 2 types of diagrams. If it couples to only muon, then you can have both the W and the Z mediated. But it couples to E or tau, then you only have the Z mediated. That's why the cross sections look different over here. And they have done studies for 3 TeV and for 10 TeV Muon collider. I forgot what luminosity they're using. But again, so you can see that you can cover a lot of open parameter space over here. And you can beat all the other future colliders here. The FCC HH is way up here, and even FCC HE, this is the electron-proton mode in the FCC, and then LHEC, I think this is also, this is probably the high energy LHC, the LHEC. I don't know if that is still on the table, but, sorry? Oh, I see. Okay, but this is probably a precursor to this LHC, FCC EH. Anyway, so yeah, so the point is that you can beat all of them over here for higher masses and for smaller couplings. Yeah. Oh, I see. I'm sorry. Yeah, maybe I should. Uh-huh.
But the interesting thing is that you also look at the offshore channel, because if you take these things, you can actually get beyond the collider.
Uh-huh. Oh, I see. Okay, so you take the end to be off cell and then it decays to leptons. I see. Okay. Okay. Yeah, I think I should add that for sure here. All right. So in this conference, I heard a few times that what can a muon collider do that other colliders cannot do. So I looked for some examples, and I found one example involving HNLs, which only the muon collider could do, but other colliders may not be able to do. And that is the distinction between the Dirac and Majorana for the HNLs. And the idea is very simple here. Let's say you're doing this collision, E plus E minus or mu plus mu minus. So just for generality, let's just call it L plus L minus. And let's look at only the final state involving L minus and W plus. Of course, you can also do the charge, the charge conjugate one, but let's just look at this particular final state. Now, if they're Dirac particles, then only the N can give you L minus W plus, and the N bar will not give you that. N bar will give you L plus W minus, right? If it's Dirac particle. But if it's Majorana particle, then you can have both these diagrams. So N can go to L minus W plus here, and here N bar is same as N if it's Majorana, then that can also go to L minus W plus. And what that does is that if you look at the angular distributions or the rapidity distribution, sorry, then for the Dirac case, you would expect this L minus W plus to be mostly in the forward region. Okay, and this is what is shown here. In this case, it's this part. For the D1 diagram and for D2 diagram, you don't have that. Now, if you have the Majorana case, then you can have it in the forward region here, or you can also have it in the backward region coming from here. So if you look at the rapidity distributions, then for the Dirac case, you would expect that your signal would be mostly in the forward region, which is what is shown by these two different curves over here. This part is forward. And if you have Majorana case, then you would expect both the forward and backward. Okay, so you expect two peaks, one peak in the forward and one peak in the backward. All right. Now, if you make the mass larger and larger, then this distinction diminishes simply because, so once this guy becomes very heavy, then it's almost produced at rest, then the forward backward won't matter much, right? That's why for a very high mass, then it's going towards the left, and then if you keep increasing this mass, then it will be just over here. But for some masses, you do have the sensitivity to distinguish between Dirac and Majorana. And they did this analysis over here, and what they found was that you can distinguish the Dirac versus Majorana. So this is for a 3 TeV muon collider, and this is for a 10 TeV muon collider. So you can distinguish up to about 2 TeV or so. But the interesting point is that you cannot go below this because of the backgrounds. Okay, so they take into account all the backgrounds and the details here, which I don't show. But if you're going below here, then your standard model background is so large that you can't really separate these distributions in a statistically significant way. So this is one example where having a high energy lepton collider can really help versus having a low energy plus E minus collider. So I believe, yeah, this probably will make a strong case for having a muon collider at higher energy. Okay. Sorry. So there you're looking for the single end production just from the Z at the Z pole, right? Yeah. But then, yeah, so then you look for the end decay. So if n is Majorana, it can decay to both L plus and L minus. Whether it's a Dirac, then it will decay to only one of them. I guess that's the idea, right? Yeah, but the point is that you can only do that below the G mass, which is very limited parameter space, right? But here you can go to very, very high mass. You mean just from the single production? Yeah, but I mean, I think the claim in this paper at least is that this part is very tricky and the background is really large. So any statistically significant distinction between these two kind of gets smeared out. But I don't know if there is a... Okay. Okay. Mhm. Uh-huh.
Angular, similar there, angular, the angle of the lepton with the rest weighted by the charge of the lepton. Depending whether it's a negative or a positive lepton, so then you combine somehow parity information and the charge information and reduce it in the P analysis. And then you can see that you get so that paper and then you can see that that you basically whenever you can discover a
But then you are working in the rest frame of the N, right? In the lab frame, this should be smeared because it will be boosted. So the distribution should be smeared somewhat, I believe. Uh-huh. Okay. So the feature still persists. Okay. Uh-huh. I see. Okay. I mean the between the dashed and the dotted ones. Don't know. Maybe because of cross section difference. Right. Yeah. Well, yeah, I don't know the the details of this plot. But okay. Yeah, so this is, yeah, go ahead. This is just the number of detected events you need in order to make a 3 sigma discovery, I believe, or 5 sigma. I forgot what they have. But yeah, this is the number of events you need to be detected. Claiming a distinction, right? Right. Yeah. And as you can see, you don't need really a lot of events. It's a handful of events, 50. So yeah, so the distinction line is the solid one, and the discovery line is the dashed and dotted one. So for the distinction, you need more events, of course, right? Yeah.
because they criticize that we only look into like here included only Dirac or only Majorana, but there's because they work a lot of these models, so they have very close Majorana.
That's correct. Yeah. Right.
Discriminated the event set that has lepton number violating and lepton number conserving.
Yeah.
What's significant can actually measure a value that is different below one. This we haven't done it.
Right. Yeah. So you have this kind of oscillation feature, right? So you have this oscillation between lepton number conserving and violating modes. I think that's what Antus showed earlier. So yeah, I think if you sit in one of those peaks for the lepton number violation, then my signal is enhanced. Then you go to the other peak, signal is diminished, and so on. Yeah. So. Mhm. Right. Right. Yeah. Okay. Yes. This one. This is the number of events detected that you would need. So if you have, yeah, if you have number of events more than 50, let's say, then you can probe this part of the parameter space. In this part here, this probably has to do, so the cross sections, if you look, the cross sections really drop. Okay, I can go back to this plot here, here, for example. So you see for 3 TeV, the cross section is actually higher for low masses than for 10 TeV. That has to come from the interplay of these diagrams. Yeah. No, sorry. So for E and tau flavor, it's just this channel. It's just the Jeep channel. Yeah, but it's just the 1 over S kind of behavior. Right, and that's what you see over here, right? But in the small it's because of the cross section. The cross section for 3 TeV is larger compared to the 10 TeV case. Right, I think so. Yeah. Right. All right. Okay. So another example which the muon collider can do, but other colliders cannot do, is this muon philic mediators. And this is something also, the features here are very similar to what Maximilian presented, and this is also in the paper. So the point is that if you have some Z prime, some vector boson which couples only to muon flavor, and one example of that is this L mu minus L tau model, where you did only at tree level you couple to the muon and tau flavor, you don't couple to the electron flavor, you don't couple to the quarks. So in that case, you can produce this particle either on resonance or off resonance, depending on what is your center mass energy. But even if you're not on the resonance, you can still have a significant deviation from the standard model case, okay, which is what is shown in this part here, or when you go to the off-cell part over here, you can also see that happening, right? So if you take this and then can do sensitivity analysis to see what is the mass and coupling that you can probe in this case, and you find that for a muon collider, and here I think we're taking a 3 TeV muon collider, that's why you see this sharp rise in the sensitivity when you go to 3 TeV, because you can produce this at resonance. So you can cover a whole lot of parameter space that is currently unconstrained. In fact, this is one of the models where essentially there is no limit beyond 100 GeV for this L mu minus L tau. Because you can't produce them directly at LHC. You need a loop process to do that. And you cannot do that at LEP because it doesn't couple to electrons at tree level. So the only constraint, the stringent constraint beyond 100 GeV is coming from this neutrino trident process. This is an old experiment called CCFR. And so this G prime mediator that will change the trident cross section, and by from the cross section measurements, you can rule out only this top corner of the parameter space, but everything else is right now allowed. And if you look at the LHC sensitivity, so the LHC, how we can do it? Well, for the high Lumi phase, what you can do the dilepton production. Let's do PP going to L plus L minus, let's say mu plus mu minus, and then from one of the muon legs, you can radiate off the G prime, and then G prime goes to 2 more muons, right? So that's the 4 lepton surge. Or you can do this at PP going to W, going to L nu, and then from the lepton, you can emit 2 leptons, that's the 3 lepton surge over here. So they can only cover a little bit better than what is currently excluded. But now if you go to this muon collider, then you increase the sensitivity by orders of magnitude. Okay. So this is another unique example where the muon collider can do much, much better compared to any other machine. Okay. Now I'm not going into the details of these different lines over here. So different final states, and then you can also include the radiative return, including the gamma, ISR, and you can do many things over there. But the bottom line is that you can probe a lot of more parameter space over here. All right. So how much time do I have? 5 minutes? Okay. So I should discuss another possibility about this Neutrino. So Richiro had this paper with his colleagues a couple of years ago, discussing this possibility at JPark. You can have up to a 1 TeV muon beam, and you can have either a 30 GeV electron beam, or have another 1 TeV muon beam colliding. So you can have mu plus option at 2 TeV, or you can have a mu plus E minus option at, I think, 346 GeV center mass energy. So this gives another unique opportunity to probe some models of neutrino physics, which otherwise you cannot do. Okay? Because this design, this particular combination is very interesting, right? So let me show you a couple of examples of that. So one example is if you have a leptophilic neutral scalar, neutral Higgs. Now you would wonder, why would that be there in the world? Well, there are models of neutrino mass, very well-known models, like the Z model. This is actually the first radiative neutrino mass model proposed in the 1980, just after the CISO. And in this model, you have this leptophilic, so it's a 2 Higgs doublet model plus a charged scalar singlet. And these 2 Higgses, they of course mix. And then you get you get 2 neutral Higgs. One of them, of course, is the standard model Higgs you can identify with, and the other one here is this other Higgs, which only couples to leptons. It doesn't couple to quarks. So there are basically not many bounds on this neutral scalar beyond 100 GeV or so. And if you have this mu plus E minus mode, then you can actually produce this at resonance. Okay. And then it goes to L plus L minus, depending on what Ikawa coupling you want to use there. And here is some sensitivity to this Neutrino in the mass versus coupling plane. So if you are producing this at resonance, then you can really probe this whole part of this parameter space. And this resonance is happening at the central mass energy, which is 346 GeV. But even if you're not sitting at resonance, you can also produce them in other different ways. You can produce them along with an association with a Z or with a photon, or you can also have a T-channel process. And this T-channel process can really take you to even higher masses than what the resonance process allows. On the other hand, if you have this photon or Z exchange, then you are here limited because you're directly producing this H. So you're limited by the center of mass energy. So you can cover, but you can cover some parameter space down in the small coupling range for smaller masses. And the shaded regions here are the current exclusions. There is one exclusion coming from muon G minus 2, and the collider exclusions are mostly coming from LEP. The LHC has very recently had a surge in this particular channel. In fact, they had an excess in the mu channel from the CMS, but also they had an exclusion, and that only covers this very narrow range around 100 GeV, 100 to 150 GeV or so. But another important point here is that in most of these kind of models, when you have coupling to off diagonals, then you would induce lepton flavor violation, right? So for example, if you have couplings to mu E and also you have a diagonal coupling to E, you would have mu to E gamma, which is very stringent, right? The bounds are very strong. But it turns out that you can have different kinds of textures here for the Ikawa coupling matrices so that you satisfy the neutrino mass, but at the same time, you avoid the charge lepton violation constraints. And that is shown by these three different lines over here called the A1, B4, and B3. So these are different textures of the Ikawa coupling for which the bounds from coming from tau to 3L, tau to E mu, or tau to mu mu E, and so on. So they exclude anything above that line. So what you see is that at least for some of the textures, like for this texture, for example, the bound coming from the lepton violation is actually weaker than the bound that you would get from collider. Okay, so muon collider can actually beat the bound coming from charge lepton violation, which otherwise naively would think that is very strong and you can never beat it if you're in off diagonal mode, but it turns out you can. So, okay, so in this particular picture, so I'm only showing the YE mu, but if you want to fit the neutrino data, you need to also have some diagonal couplings. Now you can choose which one you want. If you want EE, or you want mu mu or tau tau. If you use EE and E mu, then you'll be killed by mu to gamma. So what we do here, we use E mu, but then you set EE to 0 so that mu to gamma is safe, but then you can have mu mu and tau tau. And that's the reason why you are having constraints coming from tau LFB, not from mu LFB. And the tau LFB bounds are typically weaker than the mu LFB, so 4 orders of magnitude. So that allows you to actually probe some parameter space here, which is still not ruled out by LFB. Right. This, what color is that? Red? Yeah, the red is the resonance here that is coming from this diagram, the diagram A. So the decay width is fixed by the Ikawa couplings because it only talks to the leptons. And once you know the full Ikawa structure, then you know what is the total decay width for the edge. No. It's not like that. So this Ikawa is non-zero. I mean, we are showing only in terms of this Ikawa because this depends. So the production depends on this Ikawa. But if you want to fit the neutrino mass, then you have to include all the other Ikawas also in the fit. You can't just assume all of them to 0. Then you don't have any neutrino mass. So the idea here is that this is the title here, right? Probing neutrino mass mechanism. So you can't just arbitrarily set all the Ikawas to 0 here. Which one? Yeah, so this is, so again, so there are a few benchmarks. So that's why we're writing here B4, A1, and so on. So the rate for this process depends on some particular combination of the Ikawas, and then the other ones depend on some other combination Ikawa, right? So you can only choose some benchmark and then study what is the sensitivity. Of course, you can do a full scan, varying all the Ikawas in their allowed range, and then you can also do that. But here we're just using some particular benchmarks, and that's why I'm only showing you a line, but not like some scatter region of parameter space. Yeah. All right. Yeah. So this is one example. Another example of that is if you have a doubly charged scalar. And again, there are models of neutrino mass, very well-known models like the type 2 CISA model, where you have doubly charged scalars. And then in that case, you can use the mu plus mode of Tristan. And that will allow you to produce them at resonance again, right? You can just produce the doubly charged scalar resonance and then the decay. So again, once you don't have freedom on all the Ikawas because you have to fit the neutrino mass, so the only free parameter here is basically the mass of the doubly charged scalar and the triplet wave, B delta, because that fixes the Ikawa coupling. And the structure is fixed by the light neutrino mass matrix, basically by the PMNS mixing matrix. So these are the only two free parameters you have here. And again, as you can see over here, so if you were sitting at the resonance here, now this is for 2 TeV center mass energy. So you can exclude this part of the parameter space below this. And then if you are in the off resonance in the T channel, then you can probe Which one? The red one? No, sorry. Oh, sorry. Yeah. So this one includes both both this diagram and this diagram because they're the same. No, wait, I forgot. Probably I didn't show this one. I'm only showing that one. And then you have the ones with the gamma and the z, and they will be of course limited by just the center of mass energy. But the most stringent constraint here comes from the mu 2 gamma. This is the current exclusion, and this is the sensitivity, future sensitivity. I think 10 to minus 15 or minus 14 branching ratio. So there is some parameter space still which you can probe beyond the LAB limits over here. Okay, and then one final example I will show you is that you can also have the same doubly charged scalars in radiative models of neutrino mass, and there are a few examples like this is G-Babu model, and there is another model called cocktail model. So this is a 2-loop model, this is a 3-loop neutrino mass model. And so again, you have some sensitivity to this parameter space beyond what you can probe by using LFB. So that's the bottom line here, that there are neutrino mass models where you can allow for new parameter space to be probed at the Muon collider. Okay. So since I'm out of time, let me just go to my conclusion that the 3 neutrino oscillation is well-established paradigm, and that's now in a precision era where there are experiments probing them to unprecedented accuracy. However, that still leaves many questions unanswered in the neutrino sector, and we do need input from energy frontier. And in particular, with the high energy colliders, and especially for Muon collider, we can actually probe some new parameter space, and in principle can test the neutrino mass mechanism. So this is our Muon sort. Thank you.
We already had some questions, but if there is more, of course, we can use the time now. Just a moment.
For your heavy neutral lepton study, so if you consider some polarized beam at the Muon collider, can you improve the sensitivity?
Right. Yeah, I don't have. So in that E plus E minus paper I showed from 10 years ago, we also looked at the polarization case. For the mu plus B minus, I don't think that has been discussed. I don't know if in your paper you've talked about polarized. So yeah, in principle you can improve the sensitivity, but usually you can do that in a model where you have like a V plus A type of V minus A, V plus A type of current, right? So in the left-right model, for example, you can improve the sensitivity quite a bit. I don't know in the standard scenario if polarization really helps. I don't know. And also the other technical question would be, does the does the Muon collider have the polarization option? Because that also I am not aware of. Can you do a polarized Muon beam?
But it's when we compare the 3T data with the 3T Muon collider, because the principle is relatively similar. And the exclude or the reach curves look very different, and we first thought, okay, this is maybe something about the polarization, but it's really not the polarization. It's mostly really the Beamstrahlung plus the QED ISR, which actually leads to the fact that click is more sensitive than a 3TeV Muon collider if the neutrino is at lower masses, while the Muon collider is more sensitive at higher masses, which are closer to the collider energy, because you have basically some sort of radiative return to the neutrino production. But the polarization doesn't play much of an issue. It changes the cross section a little bit because it enhances the the T channel W production, but we saw it's a minor effect.
Exercise. Sorry, which one?
Could you go to the page before where you showed that, yeah, some plots like this.
This one?
Yeah, I mean, those are similar to me. I was confused, like, so this axis is the coupling, obviously in the other plots is delta V in the y-axis, and then the other axis, I think, is the mass. So, and then you label like different curves you plot is for different cross sections. So how do I read from this plot? So
So you're asking which part of the parameter space
yeah,
excluded?
what does that mean? So it's below that, for example, that blue curve in there.
So yeah, so anything above that can be excluded.
So above it is
Yeah,
excluded.
because this is in terms of coupling. So you can imagine that if the coupling becomes very large, then obviously you can have sensitivity to that more, right?
But
So-
how about the page before this?
Yeah, the page before is different because that's plotted as a delta, V delta is the wave, and wave, the Ikawa coupling goes at 1 over wave. Well, it goes like mass over the wave.
I see.
Okay, so that's the reason why this is why this is inverted. So anything below that would be excluded because smaller V delta means larger Ikawa coupling.
And you also assume like 95 or 68.
Yeah, I think these are the 2 sigma sensitivities. Yeah.
Thanks.
Right. And here we don't show the Ikawa for a reason because all the Ikawas are actually fixed by the structure is fixed by the type 2 seesaw. So the only free parameter there is just overall thing. And that overall thing you can just capture by the wave. That's why we don't show any Ikawa coupling here. Because you can translate the Ikawa coupling to this wave using the type 2 seesaw formula. Yeah.
And maybe just for me to remember, at these values of electron volt, the WW coupling to the triplet is very, very small.
That's very small. Yeah. So you're talking about double beta decay or something? In principle,
or
you can have
even,
double fusion. Yeah.
Kappa into 2Ws.
Right. Yeah, that will be very
That
small because the
almost-
coupling is proportional to the wave. Yeah. So for small waves, you see typically the leptonic channel that's dominant for the decay of the doubly charged. Yeah. And if you go to large waves, you need to go to like order MEV or higher wave in order to open the WW channel over here. Yeah.
Yeah.
Right.
Jürgen was asking about before the LHC limits, which are a combination of 4 Ws and 4 leptons.
So I think the limits from the 4 lepton, that's much more stringent than from the WW. So the 4 lepton limit right now is, I think, close to 1000, close to a TeV, right? That's what is shown over here. If you go to WW, then the limit is only 200 GeV or something. It's very, very weak. Yeah.
All right. So any last minute question? Then we can thank Bhupal once more.